Hello everyone. In this particular video, we will discuss about the various methods by which you can improve your efficiency of a Rankine cycle. As similar in case of a module number 2, which you have studied in the previous segment, which is known as a Breton cycle. Even there also you have discussed about the methods by which you can improve your efficiency and the work output of a Breton cycle. As it similarly in this particular Rankine cycle also, we'll be discussing the various method by which you can improve your efficiency of a Rankine cycle. But here there are totally two methods. Number one is regeneration and reheating. If you study these two methods, it's more than enough for your examination. Regeneration and reheating, these particular questions are very important in case of your examinations. They had been repeated many times, and this is the way they ask in your examination. With the help of corresponding flow and TS diagram, explain briefly the working of the practical regenerative Rankine cycle with one feed water heater. They have an expression for its thermal efficiency and overall efficiency. Okay, even that is the case they might ask. Okay, so this is the flow diagram of a practical regenerative Rankine cycle with one feed water heater. So what does it happen? What are the change are you observing when you compare this particular Rankine cycle with a normal Rankine cycle? What are the changes you are observing? The steam generator is very much similar. It has economizer, boiler and a superheater, very much similar. A turbine is very much similar. Condenser is very much similar. But this particular part, which is in blue color, like feed water heater and an extra pump also. Okay. Previously there was only one pumping work, which was from 3 to 4, and from 4 it was going directly to the economizer, correct? From 4 it was directly going to the economizer. But this particular arrangement, it has some new arrangement, like so state 5 is there, state 4, state 6 and state 7. What are this exactly? So we will try to discuss them. What happens in the normal Rankine cycle? The steam is allowed to expand from state 1 to state 2 directly. Okay, the total steam expands directly, completely to state 2, and then it is sent to a condenser. In the practical regenerative Rankine cycle, what happens at the middle of the expansion, say here the steam is there, okay, from here it goes on expanding, goes on expanding, goes on expanding, goes on expanding. At middle of its expansion, what they will do, they will take a tapping from the turbine. They will take a tapping from the turbine. In that tapping, some amount of the steam which has energy, it is not fully expanded yet, but yet it is recirculated back to the regenerator, that means steam generator. Okay, this is the way how the regeneration happens. What they will do, at the middle of the expansion, they will take a tapping from the turbine and let some amount of steam to flow back into the boiler. They will let some amount of steam to flow back into the boiler. You're regenerating, so you're generating the steam at one time, but here you are regenerating the steam. So what happens? Suppose, say, for the analysis purpose, let us assume that unit mass flow rate of steam is going here. The mass flow rate, that is kgs per second, is unit 1 quantity. Amount of steam is flowing at the inlet. What happens when you take a tapping? When you take a tapping here like this, so m1 amount of steam will flow back. M1 amount of steam will flow back. Here it was unity. When m1 amount of steam is flowing back, what is the remaining steam that is expanding from state 5 to state 2? State 5 to state 2. So here it is 1. M1 is going back, so 1 minus M1. So here it is 1 minus M1 amount of steam is expanding from 5 to 2. Okay, similarly that particular steam is existing, no other tapping here, right? So similarly that particular steam is being coming out and condensed, and that particular amount of steam, how much? 1 minus M1 amount of steam is being pumped by use of the pump number 1, okay, from 3 to 4. Okay, so this is the scenario. What happens to this tapped steam? Like it is taken from state 5, right? State 5 it has been taken. M1 amount of steam is been drawn back from the turbine and not allowing it to expand further. It is drawn back from the turbine. It is supplied to a feed water heater. What does this feed water heater do? This particular feed water heater, it heats up the steam a little bit by using the exhaust of a turbine. So whatever you can see, this particular thing, the heating procedure will be carried out by the exhaust heat, waste heat that is coming out of the turbine. So from state 5, using this feed water heater, the temperature would be raised to state 6. Okay, the temperature would be raised to state 6. From state 6 to state 7, again it is a pumping action. Again it is a pumping action. From 7 to A, it is again a economizer. A to B is boiler, B to 1 is superheater, and it goes on. So you are practically, what are you doing is you are regenerating the steam at 2 cycles. That means you are splitting up the total Rankine cycle. See, this was the normal cycle which was running, the total one. Now what are you doing is you are taking a tapping at the middle of the expansion and throwing it back to the steam generator for its regeneration. This is how it works. Let us see the TS diagram of this. So this is the TS diagram. Okay, as if you compare the previous thing and this particular thing, what happens? You can correlate the things, how the process are been going on. See, 1 to 2 was the complete expansion. At 5, you are taking the tapping for M1 amount of steam flow. Here there was a unit amount of steam flow. So 1 minus M1, so remaining it is 1 minus M1, which is flowing back to the condenser. 2 to 3 is a condenser process, correct? Now 5 you are taking tapping. From 5, what happens? 4 to 6 your feed water heater will come into picture. So 4 to 6, where is your 4 to 6? Yes, here it's your 4 to 6. Even 5 is your coming. So what happens? So 5 is coming. So 4 to 6 your feed water heater comes into picture, and 6 to 7 here you are pumping it to once again by use of another pump. So WP2 will come from 6 to 7. WP1 will come from 3 to 4. Okay, and 4 to 6 your feed water heater. And what is 7 to A? 7 to A is a normal Rankine cycle again. 7 to A is an economizer, A to B is your boiler, and B to 1 is your superheater. Okay, in the normal Rankine cycle, what we used to do is to expand the steam from 1 to state 2 directly. In the regeneration, what we'll be doing, we'll be taking the tapping from intermediate stages of expansion. From state 5, you're taking some amount of heat, that is M1, and throwing it back to the boiler. So this is how it, this is the actual meaning of a regeneration. Okay, the similar explanation for this particular thing is being given below. Please take it down in your notes neatly. Okay. See, that is what this particular note is very important. Feed water heater heats up the condensate using the heat from the exhaust of the turbine. So your heating of the feed water heater takes place from the heat which is coming out from the exhaust. You are not investing a new quantity of heat into it. You are not giving the fuel to it. You are not wasting your fuel for heating from 4 to 6. Correct? You're not giving a new quantity of fuel. What you are by the way, what you are doing? You are just heating from 4 to 6 by using the heat which is available at the exhaust of a turbine, which is available at this exhaust. This particular heat has been utilized to heat up the feed water heater. So kindly take it down. After this, heat supplied. So heat supplied is from 7 to 1. Where is the heat supplied? We can see the TS diagram. So from 7 to 1, you're supplying the heat. 7 to A in the economizer, A to B in the boiler, and B to 1 in the superheater. So total this particular process is your, what you can say, the heat supply. So how will you calculate the work done, heat supplied for this particular thing? It is heat supplied will be always taking as final minus initial, right? So final is state 1 and initial is state 7. So H1 minus H7. Okay. Here it is. is H1 minus H7. Remember, from now on, you need to multiply the quantity of the steam flow also. For suppose, from state 7 to 1, what is the quantity of the fluid which is flowing here? It is 1 unity. So if it is unity, it is 1 into H1 minus H7. So it is 1 into H1 minus H7. Similarly, heat rejected. Where will be the heat rejected? Heat rejected is from 2 to 3, correct? Heat rejected is from 2 to 3. Now, how will you do that? You have to multiply first the quantity of steam which is flowing in that particular cycle, that is 1 minus m1 into final minus initial for heats, correct? So final is H3 minus initial is H2. Similarly, here it is. So 1 minus m1 into H3 minus H2. So how will you calculate your thermal efficiency? Same thing again, efficiency of a Rankine cycle is given by net work power output divided by heat supplied, and net work is equals to net heat flow according to your first law. So net heat flow is heat supplied plus heat rejected. So just substitute the things. So QS is H1 minus H7 here, and QR is 1 minus M1 into H3 minus H2 divided by again QR is this is QS, man, just kindly change this. This is QS here. So QS is equals to H1 minus H7. So H1 minus H7, just replacing the things here to add negativity here. Okay, after that supply this particular denominator for this and this, so it will be 1 minus m1 into H3 minus H2 divided by H1 minus H7. No need to remember this expression. You can calculate the heat supplied and heat rejected, and by using this particular thing you can calculate directly. No need to remember any sort of formulas. Only the basic things which you remember is more than enough for solving the problem. Okay, even the derivation also can be done very easily from that. Now, if I want to calculate the turbine work output and the pump work, how will you do that? So let us analyze by using a TS diagram. So here, how many pumps are there? There are totally 2 pumps, correct? One is from 3 to 4. Here it is. One is from 3 to 4 and other is from 6 to 7, correct? Yes. So 3 to 4, 1 pump, and 6 to 7, 1 pump. You need to add these 2 particular pumps to get your overall pumping work. So how will you do that? So I said you, in this particular regenerative cycle, you need to multiply the steam flow with the enthalpy values. So what is the steam flow from 3 to 4? It is 1 minus m1. So 1 minus m1 into 3 to 4. Now I want work output. If I want work output, it is initial minus final. So H3 minus H4. So what is the pump output from the pump number 1? It is 1 minus m1, which is steam flow, into H3 minus H4. Similarly for the pump 2. Now you try. What is the steam flow here? m1 is the steam flow. So m1 into work output. So initial minus final. So initial is H6 minus H7. Getting it? So this is, if you add these 2 particular values, you will get the things. Now for the turbine, what you are doing here, you are expanding the steam in 2 different stages. Not in the 2 different stages actually, but the different quantity of steam is being flowing in different parts of the turbine. From state 1 to state 5, unit quantity of steam is flowing. From state 5 to state 2, 1 minus m1 quantity of steam is flowing. So how do you extract this? So total work done from the turbine is work done from 1 to 5 plus work done from 5 to 2, correct? So how will you calculate work done from 1 to 5? Mass flow rate of steam into the enthalpy values. Mass flow rate is how much? So 1 into work output, is it? So initial minus final. Initial is H1 minus H5. So 1 into H1 minus H5 is W1 to 5. Now W5 to 2, how much? So mass flow rate into the enthalpy values. Mass flow rate is how much? 1 minus m1 into initial minus final, H5 minus H2. So if you go to this particular value, so here it is, the turbine work output is equals to 1 into H